Hi guys, in this video I wanted to make a wave algorithm using the texel drawing. So um, basically so far all we have is just a line here being drawn to the center of the screen. Okay, so basically, so in this video I just wanted to make uh, simple moving waves, basically like a sine wave essentially, and I wanted to do it using texels. So I wanted to do it basically um, almost like procedural generation of the waves and then have it move based off the period every frame. So right here is where our actual logic goes. I just chose cyan for the background here. So first we flush everything to get rid of the previous draw. Otherwise things would never like get removed once we want to change like the state of it or something. And here we basically are drawing the lines that are going from 0 to whatever the pixel buffer width is, which in this case is 2000 because I chose 100,000 pixels, texels, for the, I'm not sure if this is the right word, but the granularity, essentially, for texel drawing. You can watch a video I did a while back, pixel drawing. It should be up there, where you can like kind of learn uh, how it works and everything. But essentially, it just uses texture sub-image 2D in the renderer to draw it. So basically, each frame I want to actually draw um, first the actual like body of water, and I mean this can be a constant value. So we can say, let's see here. Uh, I'll just come out here and say uh, int water body height. Um, and I'll go and set this to an on create. Uh, After we initialize, I'll set it to uh, so basically almost like a third here of the pixel buffer height. It's gonna round it, but it'll be basically be a third. And so first we're going to water body height. So we're gonna go for int I is equal to 0, I is less than water body height. And essentially inside of here, I want to do another for loop. For the pixel buffer width. And I just simply want to draw, I'll pick blue for this, so it'll be I, or it'll be J, and this will be I here. So this starts from bottom left corner. So do nano blue. We should see a darker blue at the bottom third of the screen here. And I guess instead of a third, I mean, we can do half just to kind of make it a little bit taller. So now it should be halfway. There we go. That already looks like a nice deep blue for ocean, right? Okay, so on the top part, that's where we're actually going to draw the wave. So next, we're going to actually draw the sine wave, essentially. And to do this, we need a sine wave height. 100. We'll do 100. And this means that from the actual top to the height of this wave, we're basically going to actually draw the amplitude or the sine wave essentially. So if I go to decimals really quickly, um, let's just look up. Okay, so sine wave, that's basically what we want to draw, right? Now, based off the period, that's going to determine like how big the sound wave is. So sine wave, I said sound wave. So you can see here divided by two, it's a little bit larger. If we times it by two, it's obviously smaller. So basically, I think it's fine where it's at for now. But I do kind of want to shift it. So we're gonna say like, when we shift this thing, it'll be like, uh, I think by pi. Then we want to shift it over. So we'll have to shift it based off getting like, basically taking like a degree and converting it to radians and basically adding it to like our offset and then wrapping it back around. So essentially what I want to do is, um, let's come here and just say offset. I'll call it wave offset. And for right now, I'll set it to 0. And I'll pass in sine of 2 pi. So the angle is always going to be 2 pi when we do our wave. So at each coordinate, um, we essentially want to convert whatever it is in Cartesian coordinates to our screen coordinates here. So you can see this is pi. So we want to convert this to something reasonable on our screen. And I'll say for, it'll essentially be this again. I is going to be equal now to water body height and wave end, wave top, water body height, plus wave height. Okay, so basically, I got rid of output height right there because it was redundant. But so the wave top here, water body height plus the wave height. I changed this to 50 because 100 was giving me a memory access error because obviously it's only 200 for the height, for the pixel buffer height. So basically, we just take this J value here for the width and we convert it based off. So it's like J converted is like basically in the Cartesian space here. And since we're going to pi for this actual length here, I figured it makes sense to convert it that way. So it's basically um, J converted over pi is equal to J over 100. I just picked 100 because I'm like, well, you can show um, 20 waves essentially or something like that. That was like my thinking. Somewhat, basically just any value pretty much here. The output is basically just the y based on what we pass into the sine of x. We add our wave offset, which is here, which I haven't implemented yet. And then the output gets converted back to our space. So now from Cartesian space to whatever our space is, so it'll be output over 1 since sine of x, the amplitude is 1. And basically, so the output over 1 is equal to output converted over wave height. So we just multiply wave height times the output. And obviously, we don't need to divide by 1, but I just put it here just to show that this is like the proportion that happened. Um, so then we just draw J and then we do I plus whatever that output converted is from where we were currently at. Um, so if we show it, so this is what we get here, based off what's drawn. So you see it's kind of right at the very top, so we almost had a memory access violation here. But you see it's pretty much like kind of at the top. We can make that a little bit smaller. Instead of 50, let's say we made this like a 20. And we drew it. You see now it's kind of further down there. So um, now what I want to do is basically set up the amplitude. So, or not the amplitude, but the period shift using the wave offset. So basically what I want to do for this is I want to increment by a speed variable, which I could say is like, um, I can set it to, I'll say 10. And the reason why I want to set it to 10 is because we're not going to shift over by 10. Um, Basically what this shift is going to be, and this is in degrees, but basically what this shift is going to be is, well, first let me actually just set it up here. The shift's just going to basically move it from the left to the right, and then it's going to wrap back around. So um, we're basically going to say wave offset is going to be equal to, um, or we're going to say it's plus equal to, then it's going to be the speed um, times, I guess I'll call it this angular speed. And then really this could go either way, so I can call it angular velocity. Anyways, this will be the angular velocity, and then it'll be times the, trying to think here, times 3.14159 over 180. Okay, so that just converts it to radians. Then we want to take that number and we want to actually times it by delta time. So that's what our wave offset will be. And we just want to just add this value each time. And then if wave offset greater than or equal to 2 times pi, then we get a full revolution. We'll just set wave offset back to 0. So it essentially wraps around here. And so now, if we draw it, hopefully things should start to be shifted over a little bit each frame. So you can see now things are getting shifted over each frame here. You see there's a little bit of oscillation here. You see there's a little bit of a stutter. But you see it's getting shifted over each frame. So now that we have that pretty much, then we just leave a comment here. Um, Updates the wave offset and then wraps back around to the greater. Okay. So now, as you can see, the waves, they're pretty hollow, right? So, um, we can actually do something about that when we loop through after we draw the wave. Oops. You say fill in each wave. So for this, we kind of want to go through here again. But now we want to have a couple booleans, so we can say boolean. Um, Actually, no, we want to do this for each layer. So let's kind of do this here. Boolean um, is blue, so we'll set that to false. And there's other ways to fill this in, but I was just doing it this way because it's the quickest. Um, so is blue set to false. So whenever we go through one of these coordinates in the buffer, if we can actually grab the buffer by saying let's see, here we are. So we can access this directly. So I can say pixels. So we grab a pointer to this pixels buffer. And so for this coordinate here, we don't need any of this. We can say if, and then let me just right here, draw. We essentially want to do this here. So just grab these. Up. First, let me kind of set this up a little better. So pixels, and then this will be I, J, and you could also do pixel buffer width here. I'm accessing it directly. So like I say, is equal to nano blue dot x, and then we'll just do this for the other ones here really quickly. Okay. Should be double equals. Okay. So that's equal, and I can even because pixel buffer width contains pixel buffer width here, which is um that's 500. I want 2000, so we have to do that times 4. I'll just leave it like this. So basically we just want to let me see if they want to draw so we're essentially saying so now we want to say set is blue to true. So basically we want to just set is blue equal true. So now if we say else, if is blue, then we simply want to actually draw that. And then here we actually want to say if is blue because if it's already true, that means that we've hit the spot um, where it's already true. So you want to set it back to false.